Saxon's Calculus, Lesson 81, is about derivatives and integrals of a to the x and log base a of x, and finally, derivative of the absolute value of x. So I have started off with going ahead and giving you the equation of what is happening when you are trying to derive something with an exponent. So when we have this base a, to remove it, we are natural logging it. And then because the exponent is treated kind of like the e to the x statement where it remains the same, you multiply by that same thing. So now that you have a basic understanding of the equation, which they gave you on page 398, we jump into example 1, which is find the integration of 143 to the x dx. So we're going to follow our formula here, and we know that we are going to have the 143 to the x, that's the a to the x being repeated. And then when we do the natural log of 143, because it's integrating, we end up putting it underneath. So we have the natural log of the 143 in the denominator part plus c because it was integration. So I didn't follow the formula exactly because this was the derivative and we were working backwards, but I hope you see the correlation there. Example 2. If y equals 42 to the x squared minus 5x, and they have all of that in a parenthesis, find the derivative dy over dx. So now we are taking our 42 to that same exponent of x squared minus 5x, and we're multiplying that with the natural log of the 42. You might assume that we've done all parts of this problem. However, when you're deriving, as I have stated over and over, you must derive every part, which means I need the derivative of this exponent as well. So even though I'm cramming it into the box of the former problem here, the derivative of x squared goes to 2x, and the derivative minus 5 for that part needs to be multiplying. So this is not fully in the right order. It should be ending with, yeah, I would say ending with the natural log of, although I see in their answer they kept it first, but it, like I said, it really should be at the end. All right, so then let me just make sure. 42 with the exponent, the natural log. Since they didn't really care about the order, I'm just going to leave it in that, even though I would fix the order. Example 3. Integrate, so now the opposite again, of x, a to the x squared minus 2 dx. So we know that at some point in this problem, we will have done the natural log of the base, which would be a, and we would have our original a to the x squared minus 2, multiplying with that, and then our 2x from the x squared, and now I'm comparing. So this has the x, and this part, it doesn't have the 2. So I need to be removing the 2. So that's going to be putting a half in front to remove the 2 that doesn't exist in this one. And just like before, that natural log needs to end up in the denominator. So let's make that 1 over 2 with natural log of a, which then means these parts. Now this x can't, okay, I feel like I'm intermixing the derivative and the integration again when I'm integrating, because you have to be testing it. So what I did there was a derive to see how that compared to what I was integrating. Since the x is there, it's not part of the actual answer. It's the natural piece of that. So what I'm going to have for my answer is the ax squared minus 2 in the numerator, and the 2 and the natural log of a in the denominator, plus RC. That should be it. Let me just double check it. Yes, that will be sufficient. Then part B asks us to do the derivative and integral of the log statement. So now you need another bit formula, another piece of information. So when we have log base b of x, that is the natural log of the big number dividing by the natural log of the base number. Now you should recognize that as what we did before when we did logs. Now they're just dealing with it in natural log. So example 4, if y equals log of 43 to the x plus log of 10 to the x, ran into the hole, plus log base 5 of x, find the derivative. So find y prime. So our log of 43 is going to change to natural log of the large number, which is x, over natural log of the base, which is 43. And then plus, repeat, natural log of the x over natural log of the 10, plus natural log of the x over natural log of the 5. And then I would use my calculator to find decimals for all 3 of the denominators. And I suppose, I was thinking I could do a common denominator with all of those decimals, but you could also just, once you have them, you can also just do 1 divided by that, 1 divided by that, 1 divided by that to turn them into their actual coefficients in front of the natural log. And so I would just do that. And so you should end up with 1.32 over top of your x, because the natural log of x goes to 1 over x. Yes, all right. Example 5. Find the integration of log base 23 to the x dx, So we're going to change this to our natural log of x over natural log of 23. And then we're going to find the decimal for the natural log of 23. And that is 3.14. I'll just insert it in here. And then, of course, when you do the natural log of x, you're turning it into 1 over the, 1 second. All right, the issue here with this one is I can't just treat it as 1 over the 3/4 because I have 2 parts in the problem. This is an integration by parts. So I have to, let's do our box. U will be the natural log of x. Oh, I usually don't fill that in yet. V will equal, dv will equal, and du will equal. And the other part of this, the dv part, is the dx, this piece. Okay. And that's why it's integration by parts. I've got this part and this part. So then if I'm working backwards, my v is x, And my du is 1 over x dx. Du, knew that was wrong as I did it. So now my uv gives us x, natural log of x, minus the integration of v du. The x over x becomes 1, so basically 1 dx is that part. And then, now all along in this part of the problem, I was ignoring this 1 divided by 3.14. So I'm actually having, and that is 0.32 if you do that division. That is multiplying in front of this whole thing that we're working out. So it's kind of carrying with me the whole time I'm dealing with the problem. So in my answer, I know I will have the 0.32, and then that is going to be with the x natural log of x if I distribute that. And the integration here became x, so minus 0.32x. And then obviously r plus c at the end. Now, when they wrote their answer, they still kept the 0.32 not distributed with both, but it's okay that we do. And the final section C is the derivative of the absolute value of x. So they go over some bold things here. The absolute value notation changes negative quantities to positive quantities. Yes, we remember that. Every answer coming out of an absolute value has to be positive. The absolute value notation is totally redundant if the quantities equal 0 or they're always positive. So if I have the absolute value of 4, it's redundant because we know the answer is 4. And then at the bottom of page 399, the derivative of the absolute value of a function equals the derivative of the function on the intervals where the function is positive and equals the negative of the derivatives of the function on the interval where the function is negative. So it's positive when we're dealing with positives, negative when we're dealing with negatives. That's the derivative part of that. And it just was a wordy way to say it. So in example 6 on page 400, if y equals the absolute value of x plus 2, find dy over dx. So to do this, I need to figure out the 3 sections that I'm dealing with. So one of them will be what happens when, so it's a 3-parter. So the middle one I know will be the one when it equals, when x equals. So what happens when I set this equal to 0? Well, I get -2. So this will be what happens when I get x is -2. Well, my y is 0. Then what happens when my x is greater than -2, and what happens when it's less than the -2? So using the middle one helps me find the upper and the lower boundaries for the greater than and less than. So for this one being greater than, that's where it was saying it's in its positive format. So you're going to keep y equals x plus 2. This one was the less than, so it needs to be in its negative format. So it's going to be y equals negative x plus 2. And so if I graphed those, just so you can see what that looks like, then here's my -2. I'm at 0, and then positive this direction, and of course the v is what's formed by an absolute value. Okay, so now that we have its rough sketch, the derivative of I have to do the derivative of each of the pieces. So the derivative of this piece, when I derive this, I get 1. So I will have 1 where x is greater than -2. I can't have a derivative here. It's 0, so it's not existing. And then on this one, the derivative is 1, and this makes it -1, so it's -1 where x is less than -2. And I'm debating whether I should actually say in the answer, I probably would, no exist when x equals -2. And I would box all of those 3 as the derivative of that. So then in example 7, if f of x is the absolute value of the square root of x squared minus 4, ending the absolute value, find f prime of x. So again, we know it's going to be in 3 parts. And so when I have the positive format, it's going to be, okay, that's the derivative. I don't want to put it over there. That's going to be y equals the square root of x squared minus 4. And when is that happening? When x is, and so I usually, like I said, I usually start with my center one. So where am I getting this equal to 0? Well, if I plug in 2, 2 squared minus 4 is 0, that's where I'm going to get it. So the values between 2 and -2, because this is the absolute value. So if I found 2, it's got to be both versions of it, 2 and -2. So if I start with the with that middle one, then I'm basically saying I'm not defined when x is less than 2 or greater than the -2. And then the reversed one is y equals, and it's that same square root of x squared minus 4 when, oh, and I didn't finish this statement. Okay, so here it's when x is less than or equal to the -2, and here where it's greater than or equal to the 2. So that's their split. There's their 3 sections. Now they do graph it, but I only graphed the last one just to show you, and you can look and see their graph on example 7. It's basically, there's that gap between the 2 and the -2, nothing's happening, and then it's doing a curve. But what we are doing is deriving these pieces. So when we do that, this is actually x squared minus 4 to the 1/2 if you take it out of its root. To the 1/2. And then when you derive that, you are making it 1/2 x squared minus 4 to the -1/2. And I don't like it in its negative format. But first I need to also derive this and get 2x. So I would have 2x in the top, 2 in the bottom is canceling off to leave me with, so now I can write it over here, x over x squared minus 4 to the 1/2. And I'm doing that so I no longer have it in its negative format. And I could choose to put it back in its square root. I don't know that it really matters all that much. Did they? They did. I'm not going to. It's still the same thing. And since this was the same, where'd my list go? Oh, here. Since this was the same for here and here for less than or equal to -2 and greater than or equal to 2, this is the same answer for both of those. That's the derivative for those parts. And then again, we've already kind of said it's not defined here. So the derivative doesn't exist here. I don't know, however you wish to basically say it. I would be boxing that and the none for that section. All right, example 8. If g of x equals the absolute value of the sine of x, find g prime of x. So we know, again, we're going to have our 3 sections. So to find my middle one, I am thinking my way through what happens when sine of x equals 0. And if you're picturing that you know that your center is at 0, so it's not being defined there in the center. Then what gives me sine of x? Well, that is cosine of x. And when it is a negative, I would be getting negative cosine of x because the negative is going in front of what I normally got. Yes, so those would be the two derivatives you're looking for. Oh, that should be over here with that. Then there is example 9. If y equals the absolute value of x squared minus 4, find y prime of x. Okay, so we're going to set our x squared minus 4 equal to 0. So the two numbers again that will give me that are 2 and negative 2. So in this example, I'm going to change the way I normally do that center first. And I know that I have this gap between on the graph, between the 2 and the negative 2. I also know that this is giving me a parabola, and the center would be at 0, no, sorry, at 4, 0. And so that would be like, just a second. Yes, that should, the absolute value should not change that. Oh, stars almighty. Never mind. I did say it right the first time. I'm picturing this 4 attached with the x and thinking of the absolute value as a parenthesis, but that's not what I mean. There is no number attached with the x, which is the 0, and this is the y value, which is the negative 4. So it is 0, negative 4 starting here. And then obviously, wherever I have the parabola part coming upward, between here and here, it's going to bounce to the positive section and then skew in both directions. Okay, so I'm ignoring this section between the 2 and the negative 2 at the moment, and I'm saying what happens when I derive this? Well, I get 2x, and that will be when I am from 2 upward. So I would list that as 2 to infinity. Sorry, that's kind of sideways again. And then I would be getting the same derivative, except it would be negative 2x, and that would fall from our negative infinity to negative 2, because I need to list it coming left to right. And then I need to get the middle piece. Yeah, which I just said completely backwards. Don't ask me why. These two are the same, which is these two. When it is on either of the ends, the 2 and forward and the negative 2 and down, this was the derivative. When I am in the middle piece, I was getting the negative 2x as the derivative for when I am between 2 and negative 2.